So in a previous video, I introduced the concept or the definition of linear independence. There was actually a typo here. I miswrote independence and dependence. So I introduced linear independence and dependence. I gave you a definition. So I'm going to do an example to check if the set S, which is composed of 4 vectors, is linearly independent, let's see if I can spell it right, independent or dependent. So in this kind of situation, it's actually a lot like a spanning set or linear combination question. It's just that my result needs to be equal to the 0 vector. So what I mean by that is I take my 4 vectors here, and I want to find 4 scalars. So 4 scalars. So I want to find C1, 0, 0, minus 1. 1 plus C2, 0, 1, 0, minus 1, plus C3, 0, 0, 1, minus 1, plus C4, 0, 0, 0, 1, is equal to the 0 vector, and that, in this case, is 0, 0, 0, 0. So I'm just rewriting the definition of linear independence, or not of linear independence, but how to show if something is linear independent or dependent. So I wanna solve for C1, C2, C3, and in this case C4, right over here. So what I do is I create a system of linear equations. So system of linear equations. So let's see, I'll have C1 plus C1 plus looks like nothing else, so plus 0 plus 0, 0 equals 0, and then 0 plus C2 plus 0 plus 0 equals 0, and then I'll have 0 plus 0 plus looks like C3 plus 0 equals 0, and then I'll have minus C1 minus C2 minus C3 plus C4 equals 0. So this is my system of linear equations, and already you can tell that C1 is 0, C2 is 0, and C3 is 0. And finally, from this equation here, if I substitute C1, C2, C3 as zeros, then I'll get C4 is equal to 0. So it turns out that my solution to the system will be, so usually I like to write my solution out first with a big X, and then C1, C2, C3, C4 equal 0, 0, 0, 0. In other words, this is the trivial solution. So because from this equation I get the trivial solution, so since solution is trivial, my set, you can conclude that your set, so my set is linearly independent. It's linearly independent. Okay? So let's do another example. So I want to check if is S equal to x squared plus 1, x squared plus x, and x squared plus x plus 1. So this is my set. In this case, it's polynomials. Is my set S linearly independent or dependent? So again, I want to find my scalars C, for which when I take the linear combination of these 3 vectors, I get the 0 vector. So in other words, what I'm trying to do, I'm trying to find C1 x squared plus 1 plus C2 x squared plus x plus C3 x squared plus x plus 1 equal the 0 vector. In this case, the 0 vector is just the 0 polynomial, so 0. Okay, now remember how I did this in my linear combination systems? If you didn't see those videos, then I'll just redo it. So basically what I do is I use sort of a factoring method where I first take the scalars that have 1. So in this case, C1 multiplies 1. C2 doesn't seem to multiply a scalar, and C3 multiplies a scalar, which is 1. So my first equation will be C1 plus C3 equal 0. Because actually what this is really is 0 plus 0 plus 0, where this is like 1, this is like x, and this is like x squared. But this is sort of an analogy, so all of these are 0. So don't think of it as being 1 is equal to 0. It's just I'm saying there's 3 zeros, so you can see that why I'm creating 3 linear equations. So then my second linear equation will have to do with x's. So C1 doesn't seem to have any x's. C2 does though, so I have C2, and then C3 does, so plus C3 equals 0. And then the same thing for x squared, I'll have C1 plus C2 plus C3. Okay, so this is my system of linear equations. So now let's actually put this in a matrix. So I have C1, C2, C3. In this case, I have 0, 0, 0. So I have 1, 0, 1, 0, 1, 1, 1, 1. Okay, so let's do some row reduction. So I take row 1, and I do row 3 becomes row 3 minus row 1. So that becomes 1, 0, 1. That doesn't change. 0, 0, 1, 1, 0. Then I get 0, 1, 0, 0. Okay, so now what I can do is, let's see. First I'll use this to row reduce this one. So I'll say row 2 becomes row 2 minus row 1. So what that does is we get 0, 1, 0, 0, and then 0, 0, 1, 0, and then 1, 0, 1. Okay, 0. And let's see, I'll use this one again to reduce that one. So I'll get, let's see, R1 becomes R1 minus R2. And I think you can see that what I get is the trivial solution, because as you can see, C1, so C1 is 0, C3 is 0, and C2 is 0. So what I get, so my solution is C1 equals C2 equals C3 equals 0, right? So I get the trivial solution. In other words, my set is linearly independent. Okay, so those were a couple of examples on linear independence. You can of course sometimes get linear dependence. The only thing that's different when you get linear dependence is if one of your constants, one of your scalars, so one of the variables you're solving for is not 0. So if one of your scalars is not 0, then automatically that means your system is linearly dependent.